And are there any questions from last day's work?
Oh yeah, wait, I do. You just go over like number 3.
Number 3.
Okay, 103. Actually, there was a mistake in the.
Okay. All right. Was it number 3?
No, I mean like it was switched. Like for number 2, the answer should be 0.41, and for 3 should be 55.
Oh, okay.
Switched.
Okay. You're okay with the fact that 2 and 3, the answers were switched?
Oh. Yeah,
Does that make it better for you?
Yeah.
Okay.
Never mind.
Okay, so we need to fix this. And how about the Hebden? Were the Hebden okay?
I did.
Oh. The Hebden is very helpful for Friday's test. Just letting you know.
Never mind. So I think it's the right thing. Okay.
Okay.
What is it? 2000.
Okay. Let's make sure that we're still recording the screen. Yes, we are. Okay. So we are now on page 104. So I have a microphone. Would it be helpful for me to wear it today? Or can you hear me okay? You're okay? All right. Let me know if that changes. I know the mask muffles and my voice is a little wonky. So if you do want me to put on the microphone, I can. I'm not sure I'm very good with it. It screamed at me yesterday. There was feedback. You guys know the feedback scream? Okay, so anyway, KEQ is a constant at constant temperature. What that means is that nothing changes KEQ except what? Temperature. So,
What is yellow?
huh?
What is low 3?
Page 103. Okay. It's all good. Don't worry. Yes. Oh, it's not 103. What is it? Let's see. 104. Okay. So you were right to ask. What is P103? PLO3? I don't know because we were supposed to be on PLO4. Okay. Is there anything that can change the KEQ value for a particular system? So if we have a change in concentration, do we get a shift? Yes. Does KEQ change? No. When we change the pressure, do we get a shift? Yes. But, so we get a shift, but only when? Only if gases are present and only if there's a different number of gas molecules on each side. Does it change the KEQ? No, because nothing changes KEQ except for temperature. Temperature causes a shift and KEQ changes unless delta H equals 0, but we're just going to ignore that and pretend that's not there. Okay, that's more sort of for AP. Adding a catalyst does nothing. Adding an inert gas does nothing. No shift, no change to KEQ. So only temperature will cause a change in the value of KEQ. In which direction does it cause KEQ to change? Well, if we have an exothermic reaction, so if our heat term is here, if we increase the temperature, which way does the equilibrium shift? It shifts left. And that favors the reactants. What does that mean will happen to the value of KEQ? It's going to decrease, because what's going to happen is if we have our original products over reactants, and after the shift, we shift to the left, that means we're going to have more reactants and we're going to have less products. What happened to the value of KEQ as we went from this to this? KEQ got smaller. So after the shift, KEQ is smaller. So you should be able to figure out then what happens to the value of KEQ anytime you have a reaction and you have a temperature change. Is it going to get higher or is it going to get lower? We go through the rest of them, but they're all basically the same. If you have an exothermic reaction with our heat term there, and we decrease the temperature, which direction do we shift? We shift to the right. So if we start with products over reactants, and we shift to the right, we're going to end up with big products over little reactants, right? Because we now have more stuff on the right. And so what happened to our KEQ? Our KEQ is bigger. Do you guys want to try and think your way through the next couple ones and just kind of like explain them to your neighbor? That means chat with your neighbor.
Oh.
Chat with your neighbor about it. See if you can explain the shifting and why KEQ gets bigger or smaller.
Is favoring. Yeah, it's like the other stuff. Yeah. Yeah.
Okay, so if we have our endothermic reaction and we increase the temperature, which way does it shift? We increase temperature, it shifts to the right to absorb the heat, to bring the temperature back down. And if it shifts to the right, what did we end up with more of? We ended up with more products and less reactants. So we're favoring our products, so the KEQ got bigger. Yeah? Yeah. Do we need to go through the last one? No. All right. So here's a few things to think about. Why does changing concentration not affect KEQ? We don't actually have to go through this if you don't want to. If you just want to believe me that it doesn't, we can just skip this. What do you think?
Wait, do we need to know why?
No, you don't need to be able to explain why.
Like, would it be helpful to know why?
If it helps you to understand things, to remember them, then yes, it would be helpful. So yes, shall I do it? Okay. But be aware, you do not need to explain this. You don't need to explain 1 or 2. 1 or 2. Number 3 is what we just did. Okay, number 3 is what we just did. Why does it change the KEQ? Because it shifted, blah, 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 blah. Okay, so why does change in concentration not affect KEQ? If we have our stress, which is an increase in the concentration of PCl5, then we get our shift like this. And what has happened to the concentration of PCl5 overall? Is it higher or is it lower than it was at the start? It's higher than at the start. How about your PCl3? Higher than at the start, and Cl2 is higher than at the start. That means that all of the concentrations got bigger. So if we go from PCl5, if this is our original, and then after the shift, we have a bigger PCl3, and we have a bigger Cl2, and we have a bigger PCl5. What has happened to the ratio? The ratio is the same. So that's why it doesn't change, because all the concentrations got bigger. Okay? Like I said, you don't need to be able to explain it, but yes, by the right amount, because if you actually do the KEQ math along with it, you'll see that they do. Here we're just like qualitatively, the ratio stays the same, but if you work through the math and you do all your X's and 2X's and everything, it all works out. Okay, yeah. That was a good question though. I always wonder if someone's going to ask it or if everyone's just going to believe me. Oh yeah, it's all good. Okay, why does pressure not affect KEQ? So here we have our concentration of, and you know how we've always kind of done like a little, dodgy quantities on our pressure diagram? Someone did this one and they used like the correct ones, okay? So we have, when we decrease the volume, what happened to the concentration of SO2 compared to the start? It's higher than before. How about O2? It is higher than at the start, and SO2 is higher than at the start. Does that seem like the one we just did? Yeah, so we're going to have, the ratio will remain the same, okay? They're all higher than before. It's okay, trust me, when you do the math, it works out. Because there's going to be squares, yes, and cubes and things like that, okay? Okay. Okay. Why does changing temperature change the value of KEQ? Well, there's no spike. So one side is always going to increase, the other side will decrease. That's how it always has to be. In this particular case, we made the concentration of NH3 higher, and the other two got lower. So in this particular case, NH3 got bigger, and these guys got smaller. Okay? Takeaway message, temperature changes KEQ, nothing else does. Okay? Okay. So consider the following equation. What will happen to the value of KEQ when temperature is increased? Why don't you guys try, actually, why don't you try examples 1 and 2?
AEQ will decrease. Like, yeah, because reactant of favored and products are too little. But I don't know if that's like science, you know.
What happens to KEQ when temperature is increased? Does it go up or down? It goes, everybody, down. Okay.
There's only one liquid, so does that make a difference?
Doesn't matter. The heat term takes care of everything. Okay, so let's just not worry about that. So we have our heat term here. So as temperature increases, system shifts, whoops, left to absorb heat. To bring the temperature back down. And therefore, concentration of reactants increases, concentration of products decreases, and therefore KEQ decreases. Do we need to do the next one, or were you okay? We're okay? All right. I think it's basically kind of the same here. Just the heat term is on the other side. Ooh, example 3 is different. Thank you. Oh, it's okay. She just changed blocks, so I'll deal with that. Yeah. And then, so why don't you guys try and figure out number 3? I need my grading lines. Should be right here. No, not that. Yeah, here we go. Okay. So, here, a bubble sheets. So these 3 need, they need the bubble sheet part marked. So basically just either give them a check or circle it. Don't tell them what the right answer is. Okay, so B, B, D, D.
Okay, so don't circle the right
Don't circle the right answer for them. Like say they got something wrong.
Just tick or no.
Just tick, or if it's wrong, just circle the question. Perfect, thank you. Okay. How many people think they have the answer to example 3? Anybody yet? Anyone? Not yet? Oh, I got 1. We'll get to it. I just want to give other people a chance to think. I got another one. I got 2 people who think they've got it. 3, 4, 5, 6. And I'll assume the one beside you, maybe 7. No? Yeah. Okay. Okay, so we got about, like, I don't know, how many people do we have today? 2, 4, 6, 8, 10, 12, 14, 16. We got about a third of you saying, yes, I've got it. All right, so let's take a look and see what it actually works out to be. If we increase the temperature, the KEQ increases. So if KEQ increases, which way did the equilibrium shift? The system shifted right or left? Right. And if it shifted to the right, and this was upon a temperature increase, where was the heat term? Thank you. Where did the heat term have to have been? Had to have been on the left. Therefore, the forward reaction must have been endothermic because the system shifted right to absorb the extra heat. That makes sense? Okay, so you can either from the change in KEQ predict whether it was endothermic or exothermic, or if you know whether it's endothermic or exothermic, you can predict the shift and what happens to the KEQ. Okay, do we need to do example 4? Would we like to do example 4? Anyone? Anyone? Yes? Okay. So we decrease the temperature. And the KEQ increased. Therefore, the system shifted which direction? If KEQ increased, the system shifted right. And why did it do that? It did that to absorb heat or release heat. Release heat. To bring the temperature back. Here was our stress. And there is our shift. And if it's shifting to release heat, if it is shifting to the right to release heat, where is our heat term? Heat term is on the? We shifted right to release heat.
No. It's not the.
If we go this way,
Oh,
the heat's coming out. I don't know, I just made a big mess there because that was supposed to be a highlighter, but it wasn't a highlighter. Did that make sense? Yeah? And therefore, the forward reaction is exothermic. Thank you very much. So, last thing in this section, what does the value of KEQ tell us? A large KEQ tells us that concentration of products is large and the concentration of reactants is small. Now, what do we mean by a large KEQ? Large just means greater than 1. A small KEQ means that concentration of products is small, concentration of reactants is large, and therefore your KEQ is going to be less than 1. Therefore, if you know that KEQ is greater than 1, you know that the products are favored at equilibrium. What does that mean? It means the position of the equilibrium lies towards the products, towards the right-hand side. You got more products than reactants. And vice versa. If KEQ is less than 1, you know that the reactants are favored. The position of the equilibrium lies towards the reactants. In other words, the left side, the reactant concentration is greater than the products. And not only that, if you have a larger KEQ, the more the products are favored. If you have a smaller KEQ, the more the reactants are favored. Have you heard the term yield? Yield
That like
is how much product you get. In which situation do you have a higher yield? When you have a large KEQ or a small KEQ? A larger KEQ gives a greater yield. Now, sometimes KEQ is very large. Don't worry about very large. What the heck does that mean? It just means it's really big. Okay, so for example, if we go to our data booklet, can you guys pull out your pink sheets, please? And you're going to turn to page 6. What on earth happened here? I'm going to have to redo that one. That's okay. I'll go with this one. There we are. Do you guys recognize these as dissociation equations?
what are dissociation equations?
Dissociation equations are where a substance is dissolved in water and it splits up into ions. Take a look at the first 6 acids on this table. They're in the gray zone. This is on page 6 of your pink sheet. Anybody need a pink sheet? What do we notice about these arrows here? 1, 2, 3, 4, 5, 6. They are single direction arrows, yes? And we are given a K for these things. It's called the Ka, which is just the KEQ for an acid. And do you notice what it says? It says that the Ka value is just very large, which means that it is essentially a one-way reaction. It doesn't form an equilibrium, okay? So there are reactions that are one-way reactions, and they have a one-way arrow. Everything else below that, you can see we start to have values for Ka. So there's values for KEQ, so there are products, there are reactants. And we have what kind of arrows? Equilibrium arrows. Yeah? Until we get to the very bottom. And then when we get to the very bottom, what way do those arrows go? They go this way, which means, is it possible for hydroxide to dissociate into H plus and O2 minus? Does it go that direction? No. So there are reactions that go to completion. They finish. They only go one way. There's also reactions that never start in the first place, right? Because They don't go that direction. They don't go forward. They would only go reverse if you were to put products in place. Okay? Great, that can just go in there. Okay. So if KEQ is very large, we say that the reaction goes to completion. So in other words, reactants go to products. And there will be no reactants left at the end, unless you have some excess, but that's just leftover, okay? And we have a one-way arrow. If KEQ is considered to be very small, then the reaction does not occur. So our reactants do not go to products. The reaction does not proceed. This would happen
Well, how can that happen?
if you put products, yeah? If you put them together. So the term go to completion means all reactants are transformed into products. There are some exercises here, but we're not going to do them right now because we're going to take a look at entropy and enthalpy. Page 110. Hopefully at this point, enthalpy is something that you are very familiar with. The official definition for Chem 12 is the heat content of the system. I think that's a stupid definition, so I'm never going to have you define enthalpy. Okay? Did you guys catch that? I will never have you define enthalpy because that's not a very good definition. It's kind of a crap definition. The symbol is H. Change in enthalpy is delta H. You know all of this. Here is how to think about enthalpy. Hopefully you haven't forgotten this. It is the potential energy contained in the chemical bonds. So that is the chemical potential energy. Does nature love to be at high potential energy, or does nature love to be at low potential energy? Nature loves low potential energy. So nature says, if I have a ball, it's going to spontaneously roll down the hill. That is spontaneous. If I want a ball to roll up the hill, I would have to push it. Yes? This is non-spontaneous. What does spontaneous mean? It means it happens on its own. Okay. So where does nature like to be? Does nature like to be up at the reactants? Or would it prefer to be down at the products? It would prefer to be down at the products. So as long as there is enough activation energy to get this thing going, this is going to end up at the products, all other things being equal. Okay? We call this the position of minimum enthalpy. This is where nature wants things to be. So based on enthalpy for this reaction, do we favor the products or do we favor the reactants? Products are favored, okay? Now, if it were only enthalpy that governed the world and spontaneity, only exothermic reactions would happen, yes? Why would anything ever go in the endothermic direction? Nature would say, I don't want to do that. Why would the ball roll up the hill? Right? So there has to be another driving force behind which direction a reaction goes. So before we get to that, let's just work our way through this. Nature always favors the side with minimum enthalpy. Which side of the reaction is favored in an endothermic reaction?
I mean the reverse
Which side?
of the reaction.
The reactants. How do we describe the reactants? We say they have the minimum enthalpy. Since the reactants have the lowest potential energy, minimum enthalpy favors the reactants. Note, when we say an endothermic reaction, we mean that the forward reaction is endothermic. When we say an exothermic reaction, we mean that the forward reaction is exothermic. So please decide in each of these cases which side does minimum enthalpy favor. And don't be shy about drawing a little potential energy graph if that helps you. You got them all? Matthew, you got them all? You got them all? Awesome. And like I said, in all of these cases, if you're unsure, draw a diagram. What would the potential energy diagram look like for A? Would it go up or down? It would go up. So does minimum enthalpy favor the reactants or the products? The reactants. How about for B? Where does our heat term go? Does it go in the products or the reactants? Goes in the,
Oh wait, what product?
in B.
Oh, that one, yeah.
In B?
Yeah.
So what would our graph look like for B?
That go down.
It would go down. So what does minimum enthalpy favor? Minimum enthalpy favors the products. Now C is just the same as B. And how about D? Where does the heat term go there? In the reactants. So D would be the same as A. So I'm not going to draw it a second time because that just seems wasteful. Yeah? All right. So that takes care of enthalpy. But this part is called enthalpy and entropy. Now, what you've noticed is that we favored the reactants, we favored the products, we favored the products, we favored the reactants. What do you notice about the side that is favored? The side that is favored always has the heat term. So that's a really easy way to predict it. If you can put the heat term in there, you can be like, ah, that's the side that enthalpy favors. That's the side with minimum enthalpy. Okay. So minimum enthalpy always favors the side with the heat term. Now, if you want to talk about a direction, if we look at these, our direction is that away. The favored direction is to the left. The favored direction is to the right. The favored direction is to the right. The favored direction is to the left. What type of reaction is always favored? Endothermic or exothermic? Exothermic reaction is always favored. So the exothermic direction is always favored. Don't you ever tell me about the exothermic side. What is an exothermic side? Exothermic means the reaction, which has two sides, produces heat. Is there such a thing as an exothermic side? No such thing as an exothermic side. We're going to put stars beside that. There is no such thing as an exothermic side. That's one of the most common things that people do wrong, is that they'll write something about an exothermic side. Just like one of the most common things that's also done on this test is that people will talk about the forward rate when they're actually referring to the forward reaction, right? Rate and reaction, not the same word. So be careful with your language, okay? There's a forward, there's an exothermic reaction, there's an exothermic direction. Those are what you want to use. No exothermic sides. You can say the side with the heat term because one side does have the heat term, and that's okay. Entropy. My favorite, because you get to like judge me on my, skills at keeping my space organized. Entropy is the disorder or randomness of the system. All right, and I don't know why it is represented by the letter S, but it is. I guess they ran out of letters. They're like S. Sure, let's use that. And just like delta H is change in enthalpy, delta S is change in entropy. Now, taking a look at my personal space, what happens spontaneously? More entropy or less entropy? More entropy. If I want to have less entropy, I can make it happen, but I have to put in work. Just like to get the ball to go up the hill, I would have to push it. In order to organize this space, I would have to be like, okay, this goes here. And if you're wondering what it's like in my brain and why my space always looks like, I literally have to look at every single thing and be like, oh, this is a binder clip. I know where this goes. I have to do that for every single item and like say it out loud in my brain. I know that sounds strange to say it out loud in my brain, but that's how my brain works. What can I do? It's been that way my whole life. All right. So nature tends towards more randomness. Just like it tended towards less enthalpy, minimum enthalpy, it tends towards maximum entropy. The movement towards maximum entropy is spontaneous. The movement towards minimum entropy is non-spontaneous. And here we have a kid's bedroom.
Yeah, that's my bedroom.
Spontaneously, it looks like this. So this is favored. This is not favored, although your parents may disagree. Thank you very much. Okay. So it works the same way for chemical and physical changes. Systems naturally, like if we look at this system here, this is ordered, solid, organized. Everything's in neat little rows. Everything's separated by atom type. Over here, gas. Woo, everything's roaming around willy-nilly. It's all crazy. It's very random. So to go that direction is spontaneous. Thank you very much. Yeah. So this is our second driving force. So reactions are driven by two driving forces, the drive towards minimum enthalpy and maximum entropy. So how do we know whether something is more random or not? Our first clue is to look at the state. Our largest randomness in terms of state is the gas. It is very disordered. There's lots of movement. Okay. And then we go down to aqueous, which is confined to a certain space, like gases could be anywhere in this room. If I had something that was aqueous and was in this water bottle, it would be confined to that space. That is less random than a gas, which could go anywhere. Plus, the particles aren't moving nearly as crazily. But aqueous is a mixture, and therefore it is more random than a liquid, which is a pure substance. So gas is more random than aqueous. Aqueous is more random than liquid, and liquid is more random than a solid where the particles don't really move other than to jiggle. Okay? Jiggle only. If all of the particles in a reaction are all in the same state, then you have to be like, oh, dang. Well, which one's more random? I don't know. Then it becomes the side with more molecules is favored. Okay? I don't like this break. This is a note for me. Don't write this down. More things mean a bigger mess than fewer things. Yes? Gases are vastly more random than any other state. If you can maximize the number of gas molecules, you maximize the entropy. So that is more important than anything. So when looking for the maximum entropy, you want the number of gas molecules. It is the most important. So let us try these ones here. Do you guys think do you want to try them on your own, or do you want to do them together? On your own? Okay, cool. See if you can figure out the sign of delta S. In other words, is entropy increasing or decreasing?
It-
15 halves?
That's a plus five.
Yeah.
We don't show that.
You don't need to show any of this. I'm just showing you how you would go about thinking about it.
No, but like if there's a question like this on the test, do we just write or no need to show work?
It'll probably be a multiple choice question. Okay. So let's look at the first one. On the left side, we have 2 gas molecules. On the right-hand side, we have 3 gas molecules. So which side is favored by entropy? Which side has maximum entropy? Products. So did entropy increase or decrease as we went in the forward direction? Entropy increased in the forward direction. And therefore, is delta S positive or negative? Delta S is positive. In B, we've got aqueous and solid. Which side is favored by maximum entropy? Everyone knows this one. Okay. I'm assuming that's why you're ignoring me. So did entropy increase or decrease in the forward direction? Entropy decreased in forward direction. And therefore, delta S is negative. How many minutes do we have left? Not very many. 8? Oh, that's not bad. We can finish this. Yeah, we can finish this. Okay. Solid or solid plus gas, which one's more random, right or left?
Go left. Right or left?
You mean the right.
Which one is left?
Which one is more?
Oh, we're looking at D, sorry.
Oh, okay. D for D,
Yeah.
maximum entropy. And how about C or E, max entropy? So for C, delta S is positive or negative? Positive. For D, delta S is negative because our maximum entropy was on the left. Yes. As opposed to 7.5, 7.5 is bigger than 6. And it is the gas molecules that is the most important. And finally, delta S is positive. Okay, and your homework for the day. (108) and 109? And if you did not do the Hebden yesterday, what was it? Mm-hmm. 71, 52, 34. Don't forget about this one. Okay? If you didn't do them yesterday, do them today. Okay?
However, I found in one of the lakes kinder because it will feel kind of. But still like God was like, oh my God, grab your board. And I was in go outside. Yeah, like you're right. It's very beautiful. We done like a lot. Your thinking should. I feel like we get to deep down. I would. No, no human being.
Yeah, I'm sure.
When we're seeing the program.
Never mind.